I think we can start with first speaker of this morning session, Gary Froyland. The title and the university are written on the first slide, so everyone can read. So please.
Okay, thank you very much. Thanks a lot to the organisers for the invitation to this great meeting. So lots of very interesting talks so far. Nice to be at PISA. So this is joint work with Jason Atnett, Cecilia Gonzalez-Tockman, who's in the back, and Sandro Vienti, who is here. I'll spend the first 5 or so slides doing a recap of related materials in deterministic settings. My talk is really about the random case, but we've modeled and extended some results from the deterministic case. So there is this classic spectral perturbation theory of Kelling and Lévy for transfer type operators from 1999. And one of the applications of that was to consider a closed expanding map, or generally a closed system with contracting potential, and show that if you insert small holes, then all nice species you have your measures of decay and so on persist after you puncture with the small holes. And then, I guess a decade later, Kelling and Varani considered, you can think of this result here as continuity of the peripheral spectrum, and here they were looking at differentiability of the leading eigenvalue, and in terms of open systems, one of the applications was to compute an expression of the derivative of the escape rate. So the idea is you have a small hole that you're shrinking, and as you shrink the hole, the escape rate is going to 0, and what is the rate at which the escape rate goes to 0 with respect to the hole size. And then a few years after that, Gerhard Keller had a very nice spectral theory approach to extreme value theory, and that is, all of these things we're going to expand on today, but in the random case, so not where we have a single deterministic map T, but where we have a co-cyclical map driven by some base law. Or in many cases, this could simply be some sequence of maps. Okay, so let's begin the deterministic recap. The setting I'm describing here is essentially what is in Lévy's way. So you have a piecewise map, some weight function in dV, and you construct your quenched operator in the way you've seen in many talks so far this week and last week. And you ask that T is covering in the sense that small intervals are expanded over the entire interval eventually. And from this you get, there is this contracting condition, which I don't want to mention here, but later when I get to the random settlement, I'll tell you what it is. And from this you'll get that you have a conformal measure, which is satisfying this backward eigenequation, lambda is the spectral radius, and you have your forward eigenfunction. And putting these together in the usual way, you get an invariant measure with exponential decay.
Sorry, I have to comment because it was my efficiency. I mean, this is a very nice paper, but it's just a new paper.
Okay, I will take that as a comment. One of yours here.
You're agreeing on that? Okay. I mean, the result was already in my PhD, my paper with Kelly.
Well, we use a different approach, right?
Yes, that's what I thought.
Okay, so maybe the most common situation where it's context used to this. If you take this weight to be the 1 over the derivative of the slope of the map, then the nu is just Lévy, and you can identify phi with the invariant density of your map, and to get contractility of potential, which is this, then you just need your T sufficiently expanded. Okay, so you can keep in mind this case if you like. Okay, so now to the section we want to use small holes, and this is what was done in the paper. So the idea is that trajectories will terminate when they get to this hole, and you have a open transfer operator, which is simply you kill what is in the whole, so you keep what is in the complement, and then you apply a mutual transfer operator. And so throughout the talk, I'm going to call these L epsilon, where epsilon is some measure of the size of the whole. And what they show is that as long as your epsilon holes are small enough, then all the objects we talked about will measure the eigenvalue phi. All of these things persist in altered form, but they all have the same properties. You still have the exponential decay for this mu. The mu and the formal measure are now supported on the survivor set for those points that never hold in the whole. This is now moving to right 09, a result of the differentiability of the escape rate. So now you think about what happens when the holes shrink to 0, like this. And let's say you shoot a point to take a particular case. Then you have this result for the derivative of the spectral gap, if you like. So if we take G derivative weight, the leading unperturbed value will be 1. So this is the gap, which you can think of as the escape rate. And so this will be some zero limit, but they show this is, and generically it's 1. Okay. If your C that your hole is shrinking to happens to be periodic, then you get some adjustment based on the expected gravity forward. Okay, and to round off recapping this case, briefly recap things out. This is starting very simply for people who haven't seen this at all before. So let's say you have some minor random variables, and you make a new random variable which is the largest useful so far in the sequence. And what you're interested in is the probability that this maximum that you've seen so far doesn't exceed some threshold. And you're interested in what happens and then gets very large, and so these thresholds and limit law, they should increase. Now in the RDT case, this is easy to calculate because the probability of this maximum doesn't yet exceed your ZN. This is just a product of the individual non-exceeding probabilities, which you write in terms of complements of exceeding probabilities. And now I mentioned that you need to have these ZNs going up. You want to have, of course, these things you're sending to infinity. You want these things to be decreasing. So the typical thing to do is choose this goes like T over N for some T. And now just inserting, so this is what I have here, and inserting the sum up here, T over N, then you converge to G minus T. So this is your very basic extreme value law in IID case. And now the next slide is recap deterministic extension. So where we're not IID here, but these are created by some determinists now. So we need to replace these psi j's, and the natural thing to do is you choose some observation h, real valued, and you start iterating that, and as you move along the orbit, you observe with this continuous function, and you create real numbers. And then once I do all guys involved in real numbers. So like in the law for something that is what is the probability that I choose an initial condition, so that I don't see an exceedance in an orbital Z. Okay. Again, the ZNs have to increase, and in this case, because of how I've set this up, they should increase for the maximum value of my observation. And the standard thing to do is ZN in the same way. So the likelihood that you exceed at a particular step is going up to your N. And so what Calvin does in his 2012 paper is exploit the differentiability of the leading eigenvalue, which is telling you something about the escape rate, which will be, this will be related because holes will be later identified with extreme events. This lets you get an extreme value law, whose limit is n minus theta t. And again, generic formula from the previous slide. Generic is 1. Otherwise, you have some adjustments in the case where your maximum is a single point. Okay, so if we compare this to what we had on the previous slide, here we had e minus t, and so what you can say is that generically, because this is 1, you get e minus t, generically, you have this map, the extreme value law is the same as you get for IoT, okay, which is maybe not too surprising. Yes.
And so you mentioned linear response. So what are you perturbing?
Well, the linear response is in quotes. But what we're determining here is the whole, so you have your map. And yeah. All right. So now to the random. Okay. So as I mentioned, what we have is a collection of maps. We're going to concatenate them the usual way, according to some driving map. And of course, we immediately get a transfer operator cycle from the map cycle. Okay, so we're going to develop a feminine formalism, the news, the vibes, and so on, random. And there's a lot of work on this, and I'm not going to go through this detail, but I just want to point out the main novelty that we're doing is work with discontinuous maps, because well, we need to deal with holes in order to get to the extreme value theory. And so all of this prior work on continuous maps is not immediately useful. Okay, so for a random open system, we have fiber omega, and if we map by t omega to the next fiber, and we have the whole of the next fiber, this one, then the trajectory is terminated. Okay. And so the epsilon again is just saying how big the holes are. I'm of course interested in small holes, and maybe I'll mention that Lévy, this paper is broken into two pieces. Most of it is exactly the same with a modestly sized hole, and then at the end the total result is small holes. And we use different techniques. We've extended this modest hole case to random piecewise continuous case. But today we want to look at small holes, and so we're going to ask that on each fiber, the holes are going to zero measure. That is the assumption we all have throughout.
So the population will change by 5.
Yeah, each fiber is like a copy of in our case 1, and each fiber will frequently have completely different holes. Yeah. Because later we're going to have random observations, and so it's everything random, if you like. Okay, so this is maybe the most technical slide. Do you remember here I had my L, these didn't have epsilon, so think of this as my unperturbed operator cycle. And now I have epsilons everywhere. So this is my perturbed operator cycle. And the purpose of this slide, these don't have to be transfer operators. They can just be operators that satisfy certain conditions and linear operators. And also, we don't need to have a driving on the slide, just see some sequence. Right, so we're going to ask boundaries in this way. And maybe the most strong assumption is that we may split the action like this. So we have this rank 1 projection onto random phi, and then we have the rest. So this is reminiscent of some kind of quasi-compact splitting. And the phi's, when you push them, they move, they transform to the next fiber with some scaling that I'm going to call the multiplier. And the news, they push them the adjunct, they map to the previous fiber, again with the same scale. Now we have to say that these two are close in some sense, and we do this in two ways. So one way is like this, where we think of this as a function of the dual of B And as a sine we want 0, we want this to go to 0 on each separate on each fiber. And here's a very similar way of measuring this, except instead of here we take a supreme of a unit whole. Here we evaluate specifically on these fibers, which we think of as the leading oscillator function. And what we ask is that this ratio is sine. So this should not be much smaller than this. They should be somehow commensurate in the smaller epsilon limit. This is about the decay of Q acting on phi. So if Q were not here and I was doing no iteration, this whole part here would just be delta, and I would just have delta on delta, and that would be 1. But now I'm acting with Q, and this should decay in the large in the limit. Okay. And then this last point, I don't want to say exactly what it is, kind of long, but on the next slide, and the random open map case. Okay, so if you have all these things, then you get a result which you can think of as a random quenched version of the Keller-Reinhardt result, which says that the distance between the perturbed and unperturbed multipliers on each fiber with respect to this sine delta, close operating as delta, is, well, it exists as an expression, fiber-wise. Okay, so let's reinterpret all of that, but now for random open systems. So now I think of L as being some abstract operator, but it's really a transfer operator for some closed map. The perturbed operator is the open transfer operator as I introduced earlier. In this case, delta has very easy to show that it shows that it's the multiplier closed the whole. And we ask delta to go to 0, and that's equivalent to asking that the whole measure goes to 0 on fiber. And now this Q, so the Q hat K, right, epsilon, this is what you're doing is you're starting K plus 1 fibers in the past. You are computing the probability that you're currently in the past in a hole. You iterate, you avoid all the holes, K steps, and then you land in the hole in the present fiber omega, conditioned on that last event. So these probabilities, those numbers, and what we want to assume is that as the whole string on every fiber, these probabilities converge. So we need some kind of nice behavior concerning all which has some kind of possibility. So if you have this, well, this is just, I'm just repeating what was on the previous slide. Here, on the previous slide, I had delta, but I identified that with this expression. So you can think of this as a fiber-wise derivative for the upper multipliers with respect to the whole size as you also the holes. So this is holding on each. I'm going to call this theta omega, because later it turns out that this plays the role of a fiber-wise extreme index. Okay, so now the slide is about escape rates. So I want to say a little bit about that. This denotes the, so we're on the omega fiber. We have holes of size epsilon, and I'm not a hole, I want to make a hole n steps. Okay, this is the n steps fiber set. And as you increase n, and you fix the epsilon, the measure of the set is typically decaying exponentially quickly. And so the escape rate is this exponential rate of decrease, which you get a neutral way, but in logs divided by n. And you can show that escape rate is given by the estimate of differences in logs of these multipliers, closed and open. And then Birkhoff, because we have a good driving, Birkhoff immediately gives this. So if you're driving as a dotted, then your escape rate in fact doesn't depend on the fiber that you start. And using the abstract perturbation extrapolation result, you get a formula for the derivative of this escape rate. So you might want to, as you shrink the holes, so on each fiber, as you shrink the holes, how does the escape rate behave with respect to hole size? So something like this. You want to this is going to be from 0 to 0 limit. You want to this escape rate is going to go to 0 if you shrink the holes, and of course the whole measure is going to 0. So again, we have this assumption of Q hats. We need a little bit of control on how the holes vary by fiber. So they should go like you. Of course, they're shrinking, so you have this function kappa that just decreases. And then you need some essentially bounded relationship between the holes in different fibers. Okay, so they can't be too crazy fiber to fiber. And also this quotient, which is what we have on the other slide. This should be bounded by some interval function. For this is essentially technical reasons. At some point, we want to talk about convergence and change epsilon and n. So with these assumptions, then you get that this limit exists, and you have a nice expression for in terms of the scalings t, naturally enough, and this theta that we had before. And this is 5 words. Okay. All right. So now moving toward the extreme Gaia theory. I'm using this theorem in several ways. Again, also for extreme Gaia theory. And to set out the extreme Gaia theory, I'm going to begin with a closed system. So I have a nice closed system that has a thermodynamic formalism. It has some invariant measure and trajectories in distributed coordinates. This is how I want to distribute the trajectories to generate statistics for my extreme Gaia theory. Now, saying this is actually, we realize it's not trivial for piecewise continuous case. So we started out this project, the four of us, aiming for this extreme Gaia result, but then we realized that we needed to have something like formalism, piecewise continuous maps, and that didn't exist. And then when we went back and looked at this more closely, we realized we needed actually a thermodynamic formalism for piecewise continuous closed maps. And so we have this series of 3 papers, necessarily a sequence of 3 papers exposed over an extreme Gaia theory. So if you start looking into this, this is why it seems like we have a series like this. Okay, so as I mentioned, the statistics are going to be distributed according to use the closed map. So we will have some initial condition. We start running our random per cycle closed, and then we start observing with a random observation function. So you'll start with omega fiber, you'll measure H omega, then you iterate to the next fiber, you calculate sigma omega, and so on and so on. And we want to use extreme Gaia for this random sequence of real numbers. Specifically, we want to compute the n-dose-dependency limit of this. So now you have the random observation, you have the random per cycle, and also these thresholds. These thresholds are also random. Okay, previously they don't have that depending on n. So maybe here I will pause and ask myself why random observations and random thresholds. Okay, so why random observations? Well, you can imagine many situations where the random environment that you are in is influencing the observation function. Okay, the observation function may be somehow affected by the environment it's in, so therefore you might want it to be dependent on the current external configuration of nature. As to these thresholds, okay, so here's a specific example. Let's say you're interested in statistics of water temperature, let's say, off the coast of Sydney. Now, you know that in summer water will be warmer than in winter. So if you're a climatologist, you're not so interested in the fact that the water is warmer in summer than winter. What you're interested in is how much warmer than average is it in summer, and how much warmer than average is it in winter. So what you typically do, what climatologists do, is subtract the climate mean. So, for example, on the 1st of January, you have the 1st of January for 100 or more years, and you take the mean and you subtract this from the current 1st of January. And that will give you some anomaly, how much warmer or colder you are than the 1st of January. And you can do this for the second, third, every day. Okay? So, in order to have an extreme value theory where you are adjusting thresholds depending on because here I'm thinking of omega as time passes through the year, the season. You would need to adjust your threshold depending on where you sit in the according to the seasons. Okay. To take an economic example, on the news here, economists talking about unemployment seasonally adjusted. Okay, so unemployment rates go up and down with business cycles, and economists know this, so they don't just report economic data, they seasonally adjust. So it's the same idea. On the other hand, there are cases where you might want to say to be really independent of omega. So to continue with the ocean example, let's say you're not a climatologist, but you're a marine biologist, and you want to worry about the water too warm for coral, fish, or whatever. So then you don't care that the water is warmer in summer than winter, but the absolute temperature of the water might be the animal. Okay? So it's really absolute temperature, and that kind of setting you would get rid of. You wouldn't have this because you don't care what season it is. Okay. So in any case, our theory doesn't require these two to be random, so they may be random or not random depending on the model you were trying to construct. Now, maybe I should have mentioned this earlier in the talk, but where the holes connect with the value theory is that you're going to identify sets in the base space where your observation exceeds the threshold by extreme event with a hole. So the hole at the end for a trajectory of n, that will be defined to be a set of points where the observation exceeds your level threshold. And so now the probability that your initial condition does not exceed your thresholds for n steps, that is exactly the same as the probability that your trajectory avoids holes, if we define the holes like this for n steps. Okay, so now let me show you how that very rough pieces of how the spectral works. So what we want to compute is the endosymmetry limits of this probability. And okay, so here we essentially take measures of intersections of those sets. And so we write that as integrals over products of indicator functions. And now I want to squeeze in here some iterative transfer operator, closed. And I can do that because I have a nu here, and this nu is back with variant. So if I insert an envelope cosine here, I can compensate by doing the integral in the future and dividing by the product of the multipliers. Okay, and now this, I mean, that's not obvious, but if you stare at this long enough, you'll see that this is exactly the definition of the n-step cosine open transfer operator applied to the one because the open transfer operator is killing what's in the hole, and then you iterate and kill what's in the next one, and so on. And that's exactly what we're doing here. So this is a very convenient expression for computation. And you're essentially asking how does this grow to n? And how it will grow to n is like it's leading the ultimate multipliers. And then because it's using the tables of capital Q a long way back, that capital Q will give exponentially lower returns that we can in the end neglect. So we have this ratio of cocycles of these real numbers, lambda, epsilon, and lambda, and we need to control this and see how it behaves in the n goes to infinity limit. Okay, so here's a rough idea of how one might start. If you recall back to my first corollary, I had where I was talking about random open maps. I had that the limit of this expression was equal to theta omega. The epsilon goes to 0. And what I'm doing here is just taking away the limit and saying, okay, this is approximately theta omega epsilon, which should be close to some theta. And then just by rearranging, you obtain this. And then you can interpret this as a first order Taylor expansion of x to the whole size times theta. Now, this is okay for a single quotient like this, and what we want is a quotient of products, which is the product of quotients. So to get the product of this quotient on a random orbit, what we have here is a product of exponentials, or an exponential of a random Birkhoff sum of these terms. But it's not a standard Birkhoff sum because the functions that we're averaging depend on n themselves. So the length of the sum of n, but the functions also depend on n. So you need some non-standard Birkhoff averaging, and of course you also need to show that these approximations, all these terms that we're neglecting, they will vanish, including the ones on the previous slide. Okay, so this is a very rough sketch of how things go. And at the end, here is what you obtain. So here are the main hypotheses here. You want your operators to be bounded. You want your phi's uniformly bounded above and below. And your q should decay. It doesn't have to be exponential, but at least summable. And then, if you recall back to the deterministic case, I had to choose a scaling in my whole, and the scaling depended on a little t. Now my little t can also be random if I wish. So I need to scale the whole so that I mean, if you remove all the omegas here, this would be like the size of the whole is going like t over n. But the t itself is going to be random now, and we addition have this error term that allows us to treat a few extra situations. Okay, so the large n limit, this expression that we want to compute becomes e to the minus expectation of t omega on each fiber. So in particular, in principle, the left-hand side is random, but the right-hand side is random, again, because you've got a diagram. And maybe for some context to compare this with the deterministic case, so the result from calendar 2012, if you have a single map, a single observation function, single set of thresholds, then as I mentioned, e to the minus t. So in form, it's very similar. Here you have an expectation of these now fiber-wise scaling t, and the fiber-wise string theta. So I think it's a very, I think it's a pleasant looking expression for the general random driving. This works. I can go back. Oh, it's okay. I can push the right arrow. Oh, thank you. Okay. Maybe I will skip this. I think. So we have some results about computing times, but I think given the time, maybe I'll continue. Okay, so now I had examples, and so far we've assumed the theories exist of essentially thermodynamic formalism in the open case, even, right? So the previous theorem I showed said, well, if you have these phi epsilon, etc., then you get the extreme Gaia theorem. Okay, but if you really want to work with an example, then you need to show that these things exist. Okay, so we would one path for this, I think that's the natural path, because we're talking about small holes, is that so you begin with some closed map cycle, and you show that you have a quenched thermodynamic formalism, and then you make suitable hypotheses and theories to say that if you puncture with the domains of holes, then this thermodynamic formalism persists. Okay, this would be one neat way to get this into the objects we need to apply the theory. Okay, so as I mentioned, we have this paper which does that in one. Actually, if you read the extreme value theory paper, we don't use this because we need some extra uniformities, and this one is rather non-uniform. So in fact, we went back to an earlier paper and we converted from the derivative weight to general tracking weights, the T paper, and that will give us the closed thermodynamic formalism we need. Okay. So now the main hypotheses we are T should be the usual kind of thing we have for piecewise continuous maps. Also these, I mean, it's not too bad. We need some essential, we need some uniform bounds across omega, and we need uniform covering. For the weight, again, we need some omega, and this is the contracting condition that I said I was going to talk about later. I'll tell you about it. Experts will kind of understand what's going on here, but you want this is essentially what is going to give you something like quadratic patterns. Okay, so if you like to think about the derivative case, if T is 1 over T prime, then this is equivalent to expansive along. This is equivalent to the Keller result that no, I've forgotten who was talking about that. Someone was talking about the So if you saw Roberto's talk, then this is very familiar. Okay, the whole hypotheses, again, I think not too restrictive. We just need a uniform upper bound on the number of connected components. You can have 1,000 fiber if you want some limit, and they should shrink to 0. And when they get small, then your map should be subjective, which is very reasonable. Okay, so this is an existence result for thermodynamic formalism of open systems. So you begin with a thermodynamic formalism of your closed, piecewise continuous system, and on each fiber you puncture with holes, small holes, and if the hole is small enough, then the thermodynamic formalism persists under this puncturing. Okay, so I don't know if I'm out here, but you get the random conformal measure, which is supported on your infinite survivor set. You get these forward invariant pi. You put them together to make a random invariant measure, and you also, in this case, get your random absolute continuous conditional invariant probability measure, where you're putting together the closed conformal measure and the open pi. So you can view this as generalizing the result from running Champ from a single map to a general sequence of those cycles. And a key ingredient of this is a result of the Perturbation, almost digital line, on stability of uniform hyperbolic oscillated splittings. So what we do here is we interpret the original closed cycle as a uniform hyperbolic oscillated splitting. We peel off the top space from the rest, and then when you puncture, you show this hyperbolic, and this is a large part that gives you the thermodynamic formulas of the holes. Okay, so I will finish with an example, and here's an example that I can describe fairly quickly. So let's think about balanced using maps. Beta can be whatever you like. It's not be just arbitrarily above an integer. And the reason for that is we don't want to have arbitrarily short branches because we need uniform covering. So if we had arbitrarily short branches, then those branches can take arbitrarily long to cover to expand and cover the whole. So that's the sole reason why we have this delta. Driving, whatever you like, something like a rotational circle, say. And yeah, the closed, this is as I described it, there are holes here, right? So just a random composition of beta maps. Already this is very complicated on each fiber. These five have counted within these continuities. So this we show has in a previous paper has a thermodynamic formula. Okay, now to inserting formulas. So with this particular map cycle, actually you can choose the holes very freely. I mean, they just need to be small and not arbitrarily many of them on a particular fiber. So I mean, you can really put them anywhere. And then theorem C would say, okay, your thermodynamic formula persists after you find each fiber with these small holes. All right, now on the Gaia. So the other remaining thing to consider are these Q hats, because they feature in they give us the theta, and that features in the right-hand side of that features in the limiting law. Okay, so usually in this game, you have to if you have no other means of evaluating these things, you just do them by hand. And so since I have a limited time, let me describe this situation where you do it by hand. So let's think about observation functions that have a maximum of x is 0. Okay, so my observation functions be whatever they like, but the important thing is they have a maximum at this common fixed point of all the maps, all the beta maps. Now this is a very, very simple case. And the reason I'm choosing this is so that all of these QK are 0 for K not 0. So the only one that's not 0 is Q hat 0. So this is the likelihood that you are in a neighborhood of 0 and you remain there. Okay, now to set up the extreme value, remember we need the scaling function t. We need, well, I said something about the random observation function, and we need these thresholds there. And they could all be made independent, but they may be all random. And okay, here's the theorem B for this particular example. So this is the limiting expression we want to find an expression for, and it's very horrible here. So maybe before I come back to it, let me for comparison steps for the stochastic case. So let's say we apply Keller to a single beta map, and with weight over 1 T prime. So this is what is in Keller as well. The scale pattern is just a number, and so the extreme value in that case would be like this. You would have E minus T, 1 minus 1 beta. Okay, so let's compare this. Okay, we have E minus, now we have the expectation I had before, and we have a 1 minus this minimum. And this minimum in this case is the equivalent of 1 beta. And there are two terms in the minimum. This term here is effectively coming from the slope of the mass. It's telling you how much you're expanding in 0 and how likely it is that you remain in 0. This term here this is the scaling of holes on adjacent fibers. And imagine if you're interested in trajectories that are avoiding holes, right? So if you have a hole that is, if you have adjacent holes of different sizes, the likelihood that you avoid will depend on the relative size of those holes. So you have a term here that measures the relative size of those holes. If the holes are the same size, roughly, the holes are roughly the same size, then you would pick up this would be the dominating. The holes are very different sizes, then you don't really care about the dynamics anymore. You just care about the hole size or the variation of the hole size. So that's why that is there. Okay. The zero. I mean, we're evaluating this leading equivariant function to zero because this is the maximum point of the observation function. So it was reaching a maximum at x is zero. That's why zero appears there. Okay. So I think I'm done in good time. Let me just recap what we did. So I began with this theorem. This was an abstract perturbation theorem for the behavior, the topology of the multipliers for sequence co-cycles in your operators and perturbations. And we used this a number of times, one of which was to compute derivatives of escape rates. Find the most escape rates for random dynamics with respect to the whole size. Toward the end of the talk, we developed this random variety theory where you have random co-cycles, random observation functions, and you can have either random or non-random thresholds. I skipped over this actually, but we can say something about random heating time statistics as you shrink the holes. How does the can you come up with some law for the heating time statistic? And this last theorem was the resistance theorem. So you started with thermodynamic formalism with a closed system, and you puncture on each fiber, and your thermodynamic formalism system. In the same paper, actually, we extended quenched intervals for central limit theorem, large deviation, and so on, from to general potential. We can talk about that here. And so all these things are in this paper, which has been on our file since last year. And because this is being recorded, I think I would just flash this. These are the three papers I mentioned, 1, 2, 3. Okay. And thanks very much.
Questions, comments?
So, can you comment more about the existence of your AdQ case, particularly if you have examples where they do not exist?
I think one does not come to mind where it doesn't exist. I mean, usually, I guess we should not focus on that case, but normally you focus on the case where you want to have some explicit expression for the Q case. So you can have different. You can have multiple holes. The holes might contain some holes might contain periodic points, others might contain aperiodic points. You can have different combinations like this, and you get increasingly complicated expressions for the right-hand side for your Q case. Well, two of my colleagues are here, but I think we do not look at a specific example where.
So, in principle, the problem can be generated by the position of the holes.
Yes, and interesting questions.
Other questions? Comments? Okay. If not, thank you.
Yes, I want to start by introducing the area preserving flows. So we will consider M is a compact surface, and the flow is called area preserving whenever the volume is preserved by the flow. And in this talk, we are interested in some specific flow called parabolic. And parabolic flow is defined in such a way. So whenever we have two close points, and then these points diverges in polynomial way. So this divergence is different from hyperbolic setting. So we can find some polynomial power between the divergence of 2 points. So the examples are horocycle flows and nil flows. And nil flows are flows on nil manifold. So for the algebraic setting, we can find this type of behavior. Today, I will talk about the locally Hamiltonian flow. So M is a compact surface with higher genus, and omega is a smooth area form. And we will choose a vector field X, and it vanishes at finitely many points. And locally Hamiltonian flows are the solutions of the Hamiltonian equations. So the flow can be, the flow is the solutions, and the solutions can be written as in the following way. And actually this we can find the Hamiltonian function capital H, and whenever this the flow satisfies this relation, we call it locally Hamiltonian. But actually, there is a singularity on the flow, so the capital H cannot be defined globally. So it's also called multi-valued Hamiltonian function. And locally Hamiltonian flow is also one example for area preserving flow. So this part I want to draw some picture. So we have a compact surface with higher genus, and whenever there's a locally Hamiltonian flow, then we can also consider the singularity point. So I will write the sigma from now as a singularity, and this big sigma is a fixed point. So fixed point of the flow. So this means at this point our flow stops. So whenever we have a locally Hamiltonian flow, then flow moves along the singularity, but actually near the singularity it flows very slowly. So this phenomenon gives some parabolicity. And actually at the singularity we have three types, and the first one is a center, second one is simple saddle, and the last one is multi-saddle. So the simple saddle means, so we will write m sigma. This is the number of the separatices, and this is equal to 2. And for the multi-saddle case, so multiplicity is greater than 2. And on the surface, we can, so given the singularity, we can also find that the flow trajectory that connects to different saddle points, and that is called the saddle connection. And also saddle loop is, as we see in the picture A, this is a loop, and that connects the same saddle point. And on the surface, actually, we can also find some periodic orbits. And also, there's many centers like this way. And then this part of the surface, this part of the component is called periodic component. And the rest part is called the minimal component, if the flow is the minimal on the subsurface. So I want to give some example for the local Hamiltonian flow. So actually, first case is the linear flow. So we already know the total irrational flow on the torus, but actually for the Arnold flow is a little bit different. So on the genus 1, on the torus, there's a singularity called the center type. And whenever there's a center type of singularity, then we can find the trajectory behaves some different way. So these 2 points are the close, but as time passes, this point spends much more time on the left-hand side. So we can also see some parabolic behavior. So this is, on the torus, whenever there's a center, we call the Arnold flow. And this is also picture for the higher genus case. We can see center and also other type of singularity. So now we are interested in some ergodicity and the mixing of the flow on the locally Hamiltonian flow. So for this part, we can define the closed one form eta. So I didn't specify eta, but this is whenever we have some volume form, and then eta is defined by some contraction. So here, this capital X is a vector field for locally Hamiltonian flow. So as we can see, between closed one form and the vector field, we can find the relation. And also on the space of the one form, we can also put a coordinate, and this is what the capital F means. So on the one form, we can put a coordinate, and again we can define some typicality of the one form. So for details, I will not mention too much, but in this way, at least we can define some property of the vector field. So on this surface, we can split into two parts. When the flow is minimal on the whole complex surface, or when there's a minimal component, when there's a periodic component, then we will restrict on the minimal component. So these are two different settings. So I wrote U mean and some bracket like. And in the either case, the flow is ergodic, but actually for the mixing part, it is very different. So as we saw in this kind of picture, for the minimal case, there's no center type of the singularity. So there's a more or less symmetry. So in this case, the mixing fails, but it's weakly mixing. But for the minimal component, there can be some types like central behavior. So it also can cause the mixing. But today, I will not talk about the mixing, so I will just skip this part. So I will assume the flow is ergodic, and when the flow is ergodic, then by Birkhoff ergodic theorem, the time average converges to space average as t tends to infinity. And now actually we are interested in the following. So whenever we fix the capital T, then we want to find some error terms between time and space average. So if we assume the average is equal to 0, then it's natural to guess there can be some lambda power of t, and then the integral oscillates in the following way. So there can be some lambda between 0 and 1. So actually, I want to give some remark about local Hamiltonian flows and some other related flows. So in the work of Anton Joric, actually proved in the parabolic setting, he proved that there exists some deviation bound. So here Sn of f is a nth Birkhoff sum, and then this Birkhoff sum is bounded by some constant, lambda 2 and lambda 1. So actually we will see later, but this constant is called the Lyapunov exponent of the Kontsevich-Joric cycle. But actually the Anton Joric guessed this exponent there can be other exponent as well. Here he only wrote second exponent and first exponent, but there can be more exponent, but of course we have to restrict our space of the function. And then around the same time, the Giovanni Forni proved homological equations for the area preserving flows on the complex surface. And then actually he solved some equations, and then he adapted his idea to prove the deviations for area preserving flows. So in his case, in that case, actually Giovanni could find the last Lyapunov exponent is actually positive, but each Lyapunov exponent can have some multiplicity. And actually, later also the work by Marmi Musa Yokos and Marmi and Yokos solved the homological equations for IET maths. So now we can see the relations. From the Joric, they proved the deviation, and then Marmi Musa Yokos solved the homological equations. And for the Forni's case, he proved the homological equations, and then he proved the deviation formula. So there's some orders and relations. And in 2014, Buffetov also proved deviation for ergodic integrals for translation flows. And actually, in the Buffetov's work, he used some different ways from Giovanni, and then he proved he could find some different expansions for ergodic integrals. And then he proved some limit theorem. Yeah, limit theorem. And then is 2 years ago, the Christoph Frontschek and Ulchigrai, Corina Ulchigrai also proved the deviations for locally Hamiltonian flow setting. So here, and then they proved the non-degenerate case, and non-degenerate means, so at the singularity, we have only two separatrices. And also with Christoph Frontschek and myself, we proved the degenerate case when the multiplicity is greater than 2. And also very recently, we also solved the homological equations for local Hamiltonian flows. And actually this work is also very motivated by our work, our work, and now is posted on the archive. So actually, let me just briefly introduce what is the homological equations. So homological equation is a functional equation satisfies the following relation. So here xu means the d derivative along the flow direction. And here xu is, as we can see, along the flow directions is the infinitesimal changes. So we can then integrate u of the flow minus u of x satisfies the following type of equation. And also for the flows and for the map setting, we can also consider u of tx minus u of x is equal to f. And f is called coboundary if there exists the solution u of the homological equation. And this solution also loses some regularity. It's not always true, but in parabolic setting, we lose some regularity. And I want to introduce the notion of invariant distributions. So these called invariant distribution, X invariant distributions, whenever we apply the D, then it doesn't change. So X is a derivative. You can think like derivative, and along the derivative direction, it doesn't make any change. So actually, this is a necessary condition for solving homological equations. And it's not also sufficient to guarantee the solutions. But actually, in the work of the Forney, he related invariant distributions to find the deviation formula. So as we can see, the Birkhoff integral can be approximated. It's not approximated. It can be written as a sum of the following way. So here the lambda I is a Lyapunov exponent, but in this case, this Lyapunov exponent is a little bit different from the Jorich's case. And also in the Forney's case, on the compact surface, he considered the higher derivatives at the singularity vanishes identically. So and then actually he proved the Jorich's conjecture by proving, so we can restrict our function space by taking the kernel of the invariant distributions. So whenever we take 1 to I minus 1, the kernel of invariant distributions, then we have a slow growth of the ergodic integrals. So this is the work of the Forney. And the di is Forney's invariant distributions, and each lambda I to lambda g are Lyapunov exponent. And actually, the simplicity of Lyapunov exponent is proved by Avila and Diana later, and the conjecture of Kontsevich-Jorich was completed. And this is the result of Frontschek and Ulchigrai. So now coming back to the locally Hamiltonian flow setting. And here we just assume the flow is the minimal. And when the flow is minimal, we can find, they could write the ergodic integral has a precise expansions in the following way. So they also define the invariant distributions, Forney's invariant distributions, but in the different ways. So I will explain this part later. And they also found ui of tx. This is a cocycle. And this idea is also very close to Buffetov's idea, but it's still different. And then the difference is also at the singularity, they could find the appearance of the new factor. In the previous work, in the previous part of Giovanni's work, he assumed at the singularity point, everything vanishes. But here they assumed f of sigma is not equal to 0. And then we can have some expansions. And also in this case, we also have error terms, and this error term is also uniformly bounded almost everywhere. And we can also, they could also restrict whenever from I1 to I minus 1 invariant distribution vanishes, then the ergodic integral has a slowed growth. And also this growth is determined by the Lyapunov exponent. And this one, then this is the result with Christoph and myself. And then now we consider the degenerate Setter case. And also the flow may not be the minimal. We can consider the minimal component. And the difference is we define there's a, we said there's a partial derivative, and this partial derivative doesn't vanish. So from the previous setting, we had a sum of di and ui and the error terms. But except that part, we also have other terms from the singularity. So actually, we found the existence of new invariant distributions at this singularity. So for each sigma, we defined as a partial derivative, and also for this partial derivative has a two coordinates. So invariant distribution is not only one. It's not only from the Lyapunov exponent. So there can be many more invariant distributions, and also it affects the growth of the ergodic integrals. So yeah, invariant distributions in defined by the following way. So in the local coordinate, we have x and y part. And for x part, we can add more the derivatives, and y part we can also add more derivatives. But the number of the derivative is actually bounded. It should be bounded by m sigma minus 2. So here the m sigma is actually, I want to remind you, is the number of the separatrices. So we cannot take many derivatives as many as we want. So this is the first observations. But actually this part was overcome in our recent works. And also the difference is the error terms. In the error terms, we still have a growth. The log of lim sub is equal to 0. So we can still have some subpolynomial growth. So that's the one different part from Czech and Ulrich case. Yes, I want to give some short remark. So in our work, we actually reconstructed Forney's invariant distributions. And then these invariant distributions actually could be defined by some renormalization techniques for interval exchange transformations. And for the new invariant distributions actually appear from the singularity. And this new invariant distribution appear from the is also determined by the number of the separatrices. So here I wrote V of sigma k, and this is m sigma minus 2 minus k. And here the k means the possible number of the partial derivatives. And this also new spectrum only depends on the multiplicity at the singularity. Multiplicity at the singularities. So actually, I want to talk some more about locally Hamiltonian flows. But before that, let me introduce some background. So I want to mention the T is an interval exchange transformation. So interval exchange transformation is actually generalization over circle rotations. So for circle rotations, we can write like f of x is equal to x plus alpha. Then we can write we can think like there exist two different intervals and then change their order. But for interval exchange, we generalize there can be many other intervals, and then we switch the order. So here I wrote the alpha is the elements of the alphabet, and the pi 0 and pi 1 is the permutations. So before the permutation, before applying IET, we also have some letters, and after IET, we also have letters, but it will be permuted. And each lambda means the size of the length of intervals, and almost every IETs are irreducible, and this means whenever we have some letters, whenever we have some letters, and then they don't permute. But in this case, every letter should be there's no subletters that permuted. And then for almost every lambda, the length of the intervals, then IET is minimal and ergodic. So to understand the locally Hamiltonian flows, actually we can reduce to the special flow. So this is more or less suspension flow. So yeah, the flow is defined in the following way. So here I wrote the roof function as a G, but in the picture, so you can just draw the transverse section on the surface, and then we can consider a return map. So the roof function can be chosen as a return time. So the local Hamiltonian flow actually can be understood as a special flow over IET. Yes, and then we can also consider the rho sub f in the following way. So instead of calculating the ergodic integrals, but we will choose a roof function, and then f is integrated by the flow. So if we have some long trajectory, then we can actually decompose the orbit by taking the first return, second return, and so on. But this is a locally Hamiltonian. At the beginning, as I explained, whenever we have a flow, and when it passes near the singularity, then it slows down. Of course, when it hits the singularity, it takes infinitely many times. So this is what this picture means. So for the y, it hits the singularity, red one. And in the right picture, we have a roof function, but actually roof function is unbounded. But for x, when it just passes near the singularity, the flow just slows down, but it still returns to the transverse section. So in the right-hand side, there's a picture. In the finite time, it just hits the roof. And for the last part, yes, for the Birkhoff sum, actually represents the Birkhoff integral, but it's not precisely the same because the initial point can be adjustable because we are not starting on the cross section. Also, yeah, there's also class of the function, roof function, and there's a type of logarithmic and polynomial type. For the logarithmic type, it means the multiplicity is equal to 2. So it's for the non-degenerate setting. But for the polynomial type, is a multiplicity is greater than 2. And then we introduce a new space satisfies the following. So here we define the PA in the following way, and this equation actually means near the singularity how the roof function diverges. So in the previous slide, near the singularity, it can diverges like 1 over x to the a. That is a polynomial type. But near the singularity also, it can diverge like the logarithmic way. So it tells you the difference between the two. And then we also define, so in the such space, there exist some two type of constant, C alpha plus and C alpha minus. And actually this quantity shows the limiting behavior. So when this quantity is not equal to 0, then our flow is affected by the singularity. And actually also we proved the function space PA is a Banach space by using the quantity PA at the beginning. And also we found the relation between the function and the sigma f. The rows of f. Actually, we define the row of f as a integral along the flow. So whenever there exists a singularity, then our integral is also contained in some PA space. And then we have some Banach norm. So we can more or less reduce our analysis on the surface to the IET level, for the special flow setting. And the next work is whenever we have a singularity, but in this case, our singularity vanishes. So singularity vanishes up to m sigma minus 2, and then our ergodic integral is contained in the some PB. So here the B, we can see m sigma minus 2 minus k divided by m sigma. And actually we saw this quantity actually appeared in the deviation formula. So this part actually is used in estimating ergodic integrals. So yeah, we can now reduce our analysis to IET level. And actually also in very recent work, we also could improve this type of theorem because we need some higher derivative setting. So actually this theorem can be introduced, can be extended to more general setting as well. So I want to give some brief sketch of the proof. So I will explain some cohomological equations for interval exchange transformations. So here we define some piecewise constant functions on each interval. Here I wrote D as a D is a 2G plus S minus 1. Here S is the number of the singularity. So for this cross section, we can think like some piecewise constant on each interval level. So here I also wrote H sub alpha, and H alpha is a constant function, and chi alpha is a characteristic function on each interval. And the work of the Marmi-Musayokos actually explains the following. So whenever there exists some cohomological equations, and then we can solve the cohomological equations by subtracting some function. So this is called corrections, because without correction, if we have just f is equal to u minus u composition of t, then we cannot guarantee existence of solutions, because at least we need some uniform boundedness of the Birkhoff sum for f. So we have to subtract some growth factors for f. And then, they work in the work of Marmi-Musa and Yokos, they introduced some techniques called correction operators. And then we also adopt similar type of argument in the work. So by using the idea of the correction, we will also define the generalized form of the invariant distributions. But this part is only for the Lyapunov exponent part. So I want to introduce some notations for averaging operators. And these averaging operators means this is just literally averaging. Whenever we have some interval, then we have some functions. But actually, we consider some space PA. So whenever we have some PA space, then our function can be unbounded, but still in L1. So we want to average by taking some values. And here I wrote capital M of f in the following way. So chi is a characteristic function or indicator function. And then it is written as a multiplications with chi and the averaged value. So now we can see the phi sub f can be written in the light blue. But whenever we apply the averaging operator, then this value has some mean value on each interval. So yeah, this part is a little bit technical part, but I don't want to explain too much, but let me just briefly introduce, because it's also applied in the part of the proof. So here we have interval exchange transformations, and there are several intervals. And then before before applying the interval exchange transformation T, then we have several subintervals. And then we will compare two lengths of each intervals. And then we will decide which one is larger and which one is smaller. I mean, at the end, the last intervals. And then after that, we will cut and paste and each interval. And then we can find some new intervals. That's the meaning of the I0 and I1. And then whenever we change the size of the intervals, and then this induces a new different, the interval exchange transformation. So that is written as a R of T. And then we can repeat this process the n many times. So we can see, as we can see, at the beginning we have the length 1, but after repeating the process, the length becomes small and small. And for this process, we can we can define a multiplicative cocycle. And this cocycle actually keeps the information how the interval changes along each renormalization. I mean, these following steps. And this cocycle is called Raujevich cocycle, or also Kontsevich and George cocycle. And also this picture is for the surface level, but we can also do the same thing. So we can also move the red one to the left-hand side. And then actually for the base, the length becomes smaller, but the height becomes larger. And also we will choose by repeating several times, but actually we will choose some special cocycle by choosing some subsequence. Subsequence of K, and then we will we will call it as a accelerated cocycle. This is called the Q of K. And then we will use the Q of K. And this Q of K has a Lyapunov exponent in the following way. So there's a positive Lyapunov exponent and zero Lyapunov exponent, and the negative Lyapunov exponent as well. But actually this Q of K acts on the space of the constant function. So here I wrote the splitting for RD, but actually RD is identified on the piecewise constant functions. And actually this tool is important to apply Marmi-Musayokos because we want to find some idea of the corrections. And also here I wrote H1 to HG, and also this is a basis for piecewise constant function, but so we have Lyapunov exponent to lambda I up to lambda 1, and then EI contributes to this part, and UI contributes this part. So here I chose the UI. We will choose the UI, and this means we will care about positive Lyapunov exponent from 1 to I. But the main purpose of doing this is we want to kill the effect of the invariant distributions. Basically, we want to control the growth of the ergodic integral from this part. So, and then from this part, you can see some analogy between idea of the Forni and our work. And now this one is this is called the special Birkhoff sum. So it also looks a little bit complicated, but here T of K is from the Raujevich inductions. So we have a smaller intervals from I to IK, and then for given point X, then we will add up until Q beta of K. So here the Q beta of K means it returns to the I upper K. And then this special Birkhoff sum is actually very useful because we can use it to estimate the Birkhoff sum of phi. Actually, the phi at the beginning we defined as a Birkhoff integral. So whenever we have a flow, and then we reduce this to the special flow over the IET, and then we want to count nth return time, and then this Birkhoff sum can be actually controlled by the special Birkhoff sum. Actually, this idea comes from the work of the Marmi Musa and Yokos. And in their work, they have some orbits of interval exchange transformations. And then along the Rao-Givich inductions, and then we can decompose the orbit in each steps. So here, that's the meaning of the k is from 1 to m. So whenever we have a smaller intervals, then we will add up how many orbits exist in each renormalized interval. So by decomposing the orbit, actually we can control the estimate. So now this is a part of the correction operator. So now I'm talking about this part. We want to control Sk of phi. Because now, if we can control Sk of phi, then this is more or less good, because the growth of k plus 1 is very small. It's more or less sub-exponential. So more or less you can, it's not ignoring, but compared to Lyapunov exponent, its growth is quite small. So for the correction operator part, we want to find if the growth is can be controllable by some Lyapunov exponent, then we are now good to go to apply the, so to do that, we will use the correction operators. So correction operator is actually defined by some renormalization process. So we define some special Birkhoff sum, and then we also project to the piecewise constant, and then we also project on some unstable space, and then we just return to piecewise constant. So it looks a bit complicated, but if you see, there is some conjugation between S and Q. So for Q part, we are now coming back to original interval, but applying S of L means we are renormalizing the interval, the base. And then in the middle, we just project. And also, we only want to extract some positive Lyapunov exponent. So this is the main idea. And also we can define, so whenever we define the correction operator, H sub j, and this correction operator can be written as a linear combination of the following. So here HI is the basis for the piecewise constant function. And then H sub j of phi is also already piecewise constant function, because from the renormalization process is already piecewise constant. So because HI is our basis, we can define d sub I of phi in the following way. So actually this di sub phi is responsible for the growth of the ergodic integral part. So we can define the invariant distributions, capital Di, as in the following way. So we have phi sub f as an ergodic integral, but f is a level of the surface, and we can find the relation. Actually, this part follows from the previous theorem from the previous page. And to get some estimates for the ergodic integrals, so we can see the special Birkhoff sum in the following way. Special Birkhoff sum following way. So whenever we subtract some correction operator, then the special Birkhoff sum has some slower growth. So we can see e to the lambda j times k. And then whenever the special Birkhoff sum has a slow growth, then our integral for the special flow can be also controlled by this way. So it's bounded by some lambda j and lambda 1. So this is a very brief sketch of the proof. So whenever we have some ergodic integrals, and this ergodic integral for the special flow can be bounded by some just Birkhoff sum. And this Birkhoff sum is actually controlled by the equations from the Marmi, Musa, and Yokos. And whenever the special Birkhoff sum can be controllable, then the whole ergodic integrals also controlled. But actually, in this case, I was a little bit, yeah, I only assumed the function or sigma phi is bounded. But actually, in our function is unbounded. So there's some more technical difficulty. But I just introduced the brief idea of the proof. So, okay, do I have still 5 minutes or? Okay. Yes, actually this part is only for the constructing invariant distributions from the Furness invariant distribution side. Actually, I didn't include in the slide, but actually we can also define the invariant distributions for the sections, I mean, at the singularity. So if we consider the orbit, and then whenever the orbit passes near the singularity, actually it slows down. And inside of this region, this part is more or less affected by the singularity. And we are more or less interested in calculating the integral along this side. And this type of integral is actually very related of the quantity of the C alpha. So at the beginning, I introduced the C alpha as a limiting behavior near the singularity. And actually, when C alpha is equal to 0, either 0 or not, if it is 0, then it doesn't affected by the singularity. So it means there's no, I mean, there's a singularity, but actually partial derivative of singularity doesn't affect the speed of the changes. But actually, how do we know this quantity is either 0 or not? Actually, we found some formula for calculating this quantity by some linear combinations for invariant distributions. Actually, that formula is not explicit. So only for the minimal case, we could conclude either C alpha is not equal to 0. So yeah, so this is the very brief idea for using the invariant distributions near the singularity. Okay, I will finish the talk at this point.
Okay, questions, comments?
These observables with singularities.
So okay, in the Marmi-Musayoko's case, they use the functions in the CR.
Yes.
In our case, we use some space for PA.
Yes.
Actually, we didn't solve homological equation. We used the technology of the Marmi-Musayoko's. Actually, but in our recent work, we also solved the homological equations. But actually here, you can see the function is CR. So we need some more regularity to compare this space. So we actually introduce some CR plus PA. So its R derivative is included in PA. And then along this setting, our solution is inside of R minus 1. In the Marmi-Musayoko's case, CR with some zero boundary case, and their solution has a regularity R minus 1. So that is more or less one improvement.
I see.
Further questions, comments? If not, we thank the speaker again. So we have the last talk of this session by Gaia Pozzoli of the University of Milan, Birkhoff, and the title is The Course for Random Walks in Lévy Random Media.
Good morning, everyone. And first of all, thank you to the organizers for giving me the opportunity to speak today. As you can see from the title, what I'm going to talk about is a well-established issue in probability theory concerning a certain stochastic process which is supposed to model a natural phenomenon that is anomalous diffusion. But before we go any further, let me stress that this is the result of a joint work with Alessandra Bianchi from University of Padua and Gianpaolo Cristadoro, also coming from Milano Bicocca. Moreover, this is a part of my recent thesis for the PhD program in physics at University of Insubria in Como. In order to provide a context for the topic of research, we will start with a brief general introductions on the reasons of interest for this kind of problems, and then we will move on to list previous similar models which gave rise to our specific framework. Diffusive trajectories are characterized by a short disorder motion that makes the mean square displacement increase linearly in time. And this behavior is observed in a huge number of natural systems. On the left of the top right picture, you can find a typical realization which behaves like a Brownian motion. However, in several other contexts, a super diffusive behavior can appear. The trajectory is still characterized by areas with a short disorder motion, but alternated to long ballistic paths, as you can see from the right side of the same picture. To be precise, anomalous diffusion in nature includes also a second class, probably less common, where you stay put for longer times with respect to Brownian motion, and you call it subdiffusion due to the sublinear growth in time of the variance. Typically, this super diffusive behavior is typically associated with motion in disorder media. In order to model, the basic idea is to provide analytically solvable models, which provide in order to study disorder media and non-Brownian motions, which are responsible for these anomalous diffusive behaviors, which are a topic research prompted by several phenomena, such as turbulent flows, dynamical systems with intermittencies, glassy materials, and predators are hunting for food. By way of illustration, we can mention where you can observe this phenomenon in optics, where thanks to the Lévy glass, that is a fairly new material where made up of two substances, a diffusive substrate which acts as a glue for glass spheres, where the light perform ballistic motion. Then we can mention biology with animal mobility, where the Brownian motion regime, which is included at intervals amid long linear path, depicts the exploration of a certain area due to the discovery of food. In fluid dynamics, instead, you can observe the intermittency between two different regimes, whose net effect is superdiffusion. Time segments in which the motion is ballistic are alternated to time segments in which you get trapped into vortices. The first thing you can think about is to slightly modify a classical homogeneous random walk that is the discrete time counterpart of Brownian motion and consists of a stochastic process whose trajectory is given by the summation of random steps on a certain mathematical space, which can be a Euclidean space or a lattice structure. What you can do is to consider as a jump length a sequence of random variables whose distribution is Lévy-tailed. as a power law tail decay. We call them in physics Lévy flights, since due to the since in short the tails are not exponentially bounded, and so intuitively there is a good chance that you jump really far. And this is what we mean when we say, from a mathematical point of view, that the distribution has not a finite variance. However, Lévy flights are not exactly physically acceptable because they appear to possess an infinite speed due to the infinite variance at each finite time by definition. Clearly, if spatial trajectories are completely oblivious of the corresponding time trace, then flights are legitimate. Otherwise, clearly you have some trouble. More realistic models are instead Lévy walks, where the worker needs a certain time to walk towards the new position. It is no longer an instantaneous jump, but a continuous time interpolation. Typically, the time spent is proportional to the distance to cover, so we assume a constant finite speed. To sum up to now, the main feature is that the jumps are still independent of one another. It's like placing a scatter at a random position and then removing it after the collision event. This is precisely the kind of super diffusive behavior we want to get, but it is intrinsic to the worker dynamics. It does not depend on the features of the medium, and in this sense, the model is trivial. It should be the medium and not the worker to decide how long the next jump should be. The first attempt to go beyond consists in taking into account the effects of correlation. From an applicative perspective, in the Lévy glass, you distribute the radius of the voids according to this Lévy power law distribution. In this way, you are locally modifying the density of the scattering medium, and a special correlation is induced by the topology of the environment. The mean frame path clearly then strongly depends on the position inside the sample, and the long ballistic path jumps are therefore permitted by strong density fluctuation. On the theoretical side, instead, a system involving a simple dynamics on an anomalous environment is the so-called Lévy-Lorentz gas, which is the starting point of our analysis. The focus is no longer on the dynamics, but on the complexity of the underlying network, that is the random environment consisting of fixed targets. Jumps are no more chosen randomly at each step. They depend on previous moves. For the sake of clarity, someone might have noticed that in the initial slide, I associated Lévy walk properties with Lévy glasses. I realized that this could be misleading, since clearly Lévy walks are uncorrelated. Here there is a completely different approach. Anyway, this is clarified in the reference I mentioned here, and we will comment on this later on, but we need some additional notation that we will shortly introduce in next slide. So let's finally define the two processes we will be interested in. We will focus on. First of all, what do we mean by a random walk in a random medium? It is a random walk moving on a one-dimensional irregular lattice, which consists of a random array of points, the targets, arranged on the real line in such a way that their interdistances are independent and distributed according to a common, possibly heavy tail distribution. This is what we call the random environment. More precisely, we assume that the origin is always a target and that the particle starts from there. The renewal point process that makes up the random environment remains fixed throughout the time evolution, and it is independent of the underlying random walk depicting the dynamics. As a consequence, the medium can be responsible for the presence of long ballistic flights exactly as in the Lévy flight model, but with correlations. The second process we will be interested in is the so-called generalized Lévy-Lorentz gas, that is a continuous time stochastic process obtained from the linear interpolation of a random walk in a random medium, in a Lévy random medium. This means, in a nutshell, that the particle covers the jump with unispeed. A random integer k is picked from a fixed distribution, then the particle starts to move to walk towards the k target with respect to the current position. And once the target has been reached, you repeat this action. The original definition of the Lévy-Lorentz gas is easily recovered if the underlying random walk is simple symmetric, which means nearest neighbor with equal transition probability. You can only get one step to the left or one step to the right with probabilities 50% each. Here, the model is slightly generalized by allowing longer jumps. Before we go any further, let me briefly mention a historical note. The presence of a medium with impurities and defects, which clearly cannot be simulated by a simple homogeneous model, induced the development of a new class of stochastic processes denoted as random walking random environments at the beginning of the 70s. In order to model these irregularities, two fundamental ingredients were originally introduced: a stationary random environment and a random walk whose transition probabilities determined by the environment are themselves a random function of space. The more recent random walk in a Lévy medium is a technically different yet analogous process. As for every stochastic process with a random environment, we have two ways to look at the process. In the quenched version of the process, you fix the randomness of the medium, and then you put the dynamics on this particular environment. The random walk properties are therefore determined by local quantities that do not evolve with time. If you look for quenched mathematical results, it means that you have that result for almost all the realizations of the environment. In the annealed process, instead, the annealed process instead is obtained when at any given time you consider all the random aspects of the process. So you take the average over the dynamics, but you also take the average over the medium. And this second framework is typically easier to deal with. Now, turning back to Lévy glasses, in the annealed disorder, what happens is basically that you lose the correlations. And also in quenched configurations where you have an optical thickness that is smaller than 1, you find that the uncorrelated Lévy walk provides a good approximation for the transport properties of the Lévy glass. More explicitly, whenever the average distance between two voids is smaller than the mean-free path of the scattering medium, then on average a single scattering event occurs, and the differences between annealed and quenched versions become negligible. In fact, the walker can easily explore the whole sample, and it is less sensitive to backscattering events that are correlations. Otherwise, if you by tuning the experimental parameters, the trapping effects can slow down superdiffusion. And you can observe it, for instance, in the Lévy-Lorentz gas, and more generally, it is much more relevant in one-dimensional versions because backscattering events essentially forces you to go back exactly on your track. And so there is a complete cancellation of the previous contribution to the mean square displacement and not a partial cancellation. Actually, in the main result of our paper, we will not directly deal with random walk in Lévy media, but with a slightly more general class of stochastic process with correlated increments, denoted as random walking random scenario bonds, which is inspired by the historical scheme of random walking random scenario. The original definition is the following. Suppose that a random effect is exerted on a particle wandering over the one-dimensional integer lattice. Then the motion can be identified with a random walk, a discrete time random walk on Z, whereas the random effect is mathematically described by a random scenario, that is a collection of scalar random variables associated with each side of the lattice. The quantity of interest is the variable representing the cumulative effect of the random scenario on the particle after n steps. Here we basically introduce a slight modification. Consider the composite process that we have just described jointly with the following new definition of random scenario. assume that the scenery values are labeled by the gaps between two neighboring targets instead of the lattice point themselves, and that they are also a function of the direction of motion. At each step, the particle collects the scenery values of all the bonds that have been traversed from left to right or from right to left in a single jump. Notice that in both cases, the presence of the random scenery clearly creates a dependence between the increments of the process, which is therefore ruled by a double source of randomness. Once we have introduced the model, we must explain which properties we want to analyze. Recurrence properties, limit theorems for suitable rescalings of the original process, convergence of the moments, and transport properties have already been investigated, at least to some extent, in the past years, whereas nothing has been said about fluctuation theory. By this term, in the literature, one refers to the study of the maximum of the process, that is, the maximum position reached by the walker up to a given time, and related quantities. Well-known classical results are available for partial sums of sequences of independent random variables, which is the simplest definition of an uncorrelated random walk. Nonetheless, to our knowledge, no conclusions have yet been drawn for models where the independence assumption breaks down in some way. By exploiting standard Wiener-Roth techniques, we first extended the validity of this identity for generic ladder processes for IID random walks, and then we used, in a non-trivial way, this information in order to draw conclusions about our family of random walker random scenery on bonds. So first of all, let me clarify what Spitzer-Baxter identity is. In the following, we will consider a discrete time stochastic process, a standard random walk with independent identically distributed increments, and we will refer to it as a control process. Then we introduce a second random walk, the so-called cost process, which may or may not depend on the control process. We will be interested in the characterization of the joint control cost process, which can be also thought about as a single higher dimensional process whose first component plays a special role. More specifically, we would like to characterize the asymptotic behavior of the cost process at certain specific times that we call ladder epochs. The first ladder epoch is determined by the event that the walker S goes to the right of the starting position for the first time, that is the first passage time in the positive semi-axis, and so on and so forth by induction. Notice that first passage events account for key problems in the theory of stochastic processes, since you can determine when system variables assume specific values, for instance, when the variable crosses a given threshold value. Well-known classical results concerning jointly the sequence of maxima and the associated time series written in the form of identities for the joint generating functions are available for sums of independent random variables. And notice that the passage from the original Markovian sequence to the reduced non-Markovian sequence of maxima leads to a higher order of complexity despite the lower number of distinct elements. Anyway, with a minimal effort, we can extend the validity of the identity to generic cost associated with the IID random walk. This generalized Spitzer-Baxter identity that we are going to discuss will enable us to infer information on our family of random walk with correlated increments. The generalized Spitzer-Baxter identity for the joint generating function of tau S tau C tau tells you that their distribution stem from the knowledge of quantities on the right-hand side that do not depend on the first passage event, and that's a crucial point. Then clearly one wants to write the right-hand side in such a way that you can perform computation in practice. As a first comment, let me stress that this first step is quite trivial. You just have to retrace the original proof with a Wiener-Roth argument. It is worth comment on the benefits of this generalization. In the first instance, we should ask ourselves when this identity is useful from an operational point of view. We can infer on the tail asymptotic of the cost process if some symmetry property is assumed. The cost process must be given by a symmetric and an antisymmetric component, or just one of them, with respect to the control process. In particular, the latter includes the original Spitzer-Baxter identity as a special case. In the presence of a purely symmetric cost process, the Spitzer-Baxter formulation can be improved and provides an explicit representation for the characteristic function of the first ladder cost jointly with the first ladder epoch. It is a closed identity which depends on the characteristic function of the cost increments and possibly also on the properties of the control process. In fact, the capital Phi takes into account an eventual correction factor due to the presence of a lattice structure for the random walk S. If its increments are picked from a continuous state space, then clearly the integration domain Sn equals 0 as 0 measure, vector Phi is equal to 1, and the asymptotic behavior of the cost process becomes universal in the sense that the dependence on S can only come indirectly through the eventual correlation between cost and control processes and not directly, not explicitly. In addition, by setting S equals 0, we recover a historical result that is the classical Sparre-Anderson identity for the first ladder epoch, and the first passage probability to the positive half line for a symmetric random walk decays with a power law universal exponent. Moreover, recall that if you consider a continuous jump distribution, the coefficient is also independent of the exact form of the probability density function of the displacement per step, and even of whether the moments of this displacement exist. Now, turning back to the general identity star, it is not difficult to realize that the tail asymptotic of the cost process is readily determined by the asymptotic expansion of the characteristic function of its increments around 0, which account for the tails of etas, and by applying Tauberian theorems. Notice that we have complete control both on the exponent, the constant of proportionality, and the balance of the tails, since star is a closed form expression. Anyway, the complete characterization for a generic cost cannot be briefly summarized. So here I just mentioned an example that we will need for our purposes. The first ladder length is the collection of the absolute values of all the jumps that have been performed by the walker up to the first passage time. Notice that with this choice, the cost process is strictly related to the control process, which consequently inherits the symmetry property. A less exhaustive result can be derived for antisymmetric costs. Exactly as before, the proof follows by setting Z equal 1 and by performing a series expansion around S equals 0. In fact, we know that the characteristic function of plus and minus C tau have the same leading order term, except for the complex constants that are complex conjugate by assumption of antisymmetry. The lack of a closed identity means that you have to pay a price. You get a complete characterization if and only if the cost is one-sided, and in any case, you have to exclude the limiting case of the domain of attraction of a normal law. As in the previous case, in the presence of correlations between control and cost processes, the former must be symmetric. As an outstanding example of odd cost function, we have the first positive maximum, as in the Spitzer-Baxter original result, which is also known as first ladder height or leapover. This is a fundamental quantity, in particular for jump processes with heavy tail steps. In fact, it is the distance that the walker overshoots the origin in a single jump, which gives you a measure of the ability to crisscross a point. In jump processes, when in the presence of an infinite variance for the jump distribution, the first arrival at a given target position is lower than the first passage. Since in contrast with the narrow jump distribution, when they are essentially equivalent, it is very likely that you crisscross the point multiple times. And this is important, for instance, for the understanding of how far proteins or tracers searching for their binding site overshoot the target. At this point, one may have lost the thread. So why we focused on this generalized Spitzer-Baxter identity for symmetric and anti-symmetric costs? We will show in a few minutes that we can characterize the asymptotic behavior of a random walking random scenario on bonds by simply knowing the tails of two quantities associated with the underlying random walk S that are the Lipover itself and not directly the first letter length, but its difference with the Lipover. For the moment, just trust me on this, then we will discuss the sketch of the proof. As a footnote, notice that this linear combination is precisely the continuous first passage time of the Lévy walk obtained by linearly interpolating the random walk S. So the very last ingredient of this first step is the following lemma, which enables us to deal with the generic linear combinations of L tau and S tau for IID random walks. This result can be proved in two different ways, by means of the usual expansion of the generalized Spitzer-Baxter identity with both a symmetric and an antisymmetric component, or by introducing a probabilistic tool that determines the tail behavior of a linear combination of two correlated random variables on the basis of the knowledge of their marginal asymptotic characterization. We will come back to this later on, since it is essential for random walking random scenario on bonds. As a final comment, let me stress that up to now, we only talked about first ladder epoch and value, but the extension to the entire ladder process is immediate, since due to the renewal structure of the process, you can the ladder variable of order R can be seen as the sum of n IID first ladder quantities. So now we are sufficiently equipped to really get to the heart of the issue. Let me briefly recall the notation. We associate two random variable descending values zeta k plus and minus to each bond of Z, and then we consider also an IID random walk on Z, which collects the scenario values of all the bonds that it traverses. This collection is what we call the cost process for at each finite time. And exactly as before, we wonder about its probabilistic features at the first passage time. Here is a shortened version of our theorem. By assuming that the increments of the underlying random walk and the scenario values are in the domain of abstraction of a stable random variable with index respectively beta and gammas, we can infer on the asymptotic behavior of the cost process, or at least provide useful bounds on it, in terms of an exponent of the power law decay rho, which interlaces between the two sources of randomness. For the sake of clarity, let me recall you that whenever the stability index is equal to 2, we have the classical central limit theorem with the domain of abstraction of normal law with finite mean and variance. When the stability index is greater than 1, then we have a limiting stable distribution with infinite variance and a power law tail decay, which remains valid also for a stability index smaller than 1, when also the finite mean, the mean value of the distribution is infinite. As you can see from the statement, whenever the scenario values have a finite mean distribution, then the characteristic exponent characterizing the tail asymptotic of the first ladder cost is ruled solely by the properties of the underlying random walk, the dynamics. Moreover, I want to anticipate that this result is obtained for in the annual setup by taking the average over the random scenario. The quenched configuration, which I recall you corresponds to the probabilistic time evolution in a fixed realization of the random scenario, remains an open problem due to the higher degree of complexity with respect to the annual setup, where instead one observes the effects of averaging over several processes evolved in all possible arrangements of the scenario values. The challenge would be to prove an analogous statement valid for the quenched law and for almost all the realizations. Very quickly, here is the complete version for a couple of comments. Firstly, in spite of the presence of correlations, the theorem can be stated for a ladder cost of all orders, since in the end, you can rely on the renewal structure of the underlying random walk. As we already anticipated, all that matters are the first ladder length and leapover of the IID random walk. Secondly, non-matching bounds and additional assumption can appear, additional stability assumption can appear in the most complex situation, that is in the presence of an infinite mean distribution for the scenario values. Anyway, we are going to emphasize the tricky point later on. Let me briefly explain the three fundamental ideas that make up the argument of the proof. First of all, the asymptotic behavior of the cost process is derived from the corresponding asymptotic expansion of its characteristic function. So, in the first instance, one needs to find a convenient rewriting of the cost process. And in order to do so, we introduce the notion of local times, that is the number of times that you pass through a gap between two neighboring targets by keeping the bond, by keeping also track of the direction of motion. In this way, the cost process can be easily written as the sum of the scenery values multiplied by the corresponding local times. Furthermore, if we consider the first passage time, then local times towards left and right in the negative semi-axis are balanced, since if you go there, then you have to come back to the origin, whereas in the positive semi-axis, you have only the right component of the local times, which coincides with the indicator function of the leapover by definition of first passage. In order to see why this is useful for the annealed setup, we can apply a common trick in probability theory, that is the law of iterated expectations. In short, we are partitioning with respect to different realization of the underlying random walk. And at this point, taking the average over different scenario values, it is clear that it is a crucial point. We would be in trouble with a quenched configuration. To sum up, by embracing all the random aspects of the process, we can, in spite of the presence of correlations, we can exploit results deriving from the generalized Spitzer-Baxter identity for IID random walks. And in fact, for the moment, we brought the result in terms of characteristic function of the distribution defining the scenario values, and the underlying random walk observable started to appear, at least in the second term of the product. As a second point, we have to make explicit the first term in order to recover the linear combination of L tau and S tau. What we can do is to exploit once again the small s expansion of the generating function of the scenario values and the exponential approximation. For the sake of simplicity, for the moment, let us consider a finite mean case. We will comment on infinite mean distributions at the end, nothing changes. In this way, we wrote the argument as the product of two random variables, Z1 and Z2, whose expectations coincide with the generating function of the two quantities that associated with the underlying random walk that we already studied in the step 1. If you don't worry about the random error appearing in the first exponential, trust me, we will fix it soon. Then basically we are done. In fact, due to the particular form of the random variable zeta case, we can conclude by means of a very clear lemma. We can infer on the asymptotic estimate of the joint generating function on the basis of their marginal characterizations, since we can control the covariance term by means of the Cauchy-Schwarz inequality. In fact, by definition, the expectation of the product of two complex random variables is given by the product of the expectations plus their pseudo-covariance. The only doubt could be why the one-sided assumption on the scenario values and the generating function formalism. Well, in principle, you could also keep the characteristic function, but then you have to split real and complex exponential and iteratively apply the lemma. And if you try to do this, then you get some trouble. Thirdly, and finally, we have to show that the random error can be handled by means of the definition of little o, the triangle inequality, and the law of total expectation. It is not difficult to realize that the expectation of Z1 can be written as is asymptotically equivalent to the generating function of the product of two independent random variables, one carrying information about the random scenery and the other about the underlying random walk. But this is a well-known result in probability theory, and so this basically ends the proof. Before describing the applications, let me briefly clarify the technical assumption in the statement of the theorem. First of all, whereas the limiting case beta equal 1 is permitted for the underlying random walk, the Cauchy domain of attraction for the scenery values must be excluded. And this is due to the fact that when you compute the generating function of the scenery values at a point with the local times in the argument, then we are not able to cope with the logarithmic term. Secondly, what is more challenging in the presence of infinite mean distributions? Basically, we have to control the sum of the local times raised to a certain power in terms of the underlying random walk observables. And in this case, we are no longer able to provide a direct estimate on the expectation of Z1. This step should be improved, otherwise we have to give up to the precise Bayesian of attraction of the cost process, and we are forced to require an additional stability hypothesis, a stronger stability hypothesis in certain subcases. Now let's go back to the specific case of a random walk in a Lévy random medium, that is a coupled process where a standard random walk performs its jumps on an independent random array of targets. This is a special case of a random walk in random scenery on bonds, where the random scenery accounts for the presence of the random environment. We first characterized the tail distribution of the maximum as in standard fluctuation theory results, and then we also consider the total length of the trajectory up to the first passage time. This second example has been chosen since, in turn, it can be used jointly with the first one, can be used to infer on the law of the continuous first passage time for the generalized Lévy-Lorenz gas, as we will see in the next slide. Whereas the first example is instructive since in the absence of the even part of the scenery values, the proof greatly simplifies. You just need key point 1, that is the annealed setting, or equivalently the decoupling of the two sources of randomness. In short, you just have to compute the generating function of the leap over of the underlying random walk at a point that depends on the parameters of the random medium, in particular the power law exponent gamma. Notice that the case gamma greater than 1 is in a sense a trivial result, since intuitively you can think about it as a regular homogeneous lattice whose lattice constant is related to the finite mean, the mean value of the distribution. In fact, the anomalous behavior can only come from the heavy-tailed dynamics, and this is intrinsic to the Walker dynamics. And this is in contrast with the case of an infinite mean distribution for scenery values, where instead you represent a highly disordered and inhomogeneous medium. The continuous time interpolation is also an enlightening example. In this case, the definition of the scenery values is based on a very simple intuitive idea. Since in the jump process you can overshoot the origin in a single jump without hitting it with instantaneous jump, whereas in the continuous time process you are forced to pass through it. Then you can rely on the following trick. You have to overlook steps to the right and count the jumps of the steps to the left twice. In this way, you remain only with the even part of the scenery values, which is in a sense complementary with respect to the case of the maximum. And in this way, we can avoid the additional stability assumption, although upper and lower bounds on the continuous first passage time still may not coincide. So, by way of conclusion, we can say that we are fairly pleased with the general outcome, although maybe one could aspire to do better with regards to highly disordered environments. One should try to improve the bounds by means of a finer control on local times of the underlying random walk, at least to completely relax the hypothesis of stability due to technical issues in the computation of the lower bound. Non-trivial probably not easy problem is concern an analogous statement for a quenched version of the model that I call you is a result that must be true for almost all the realization of the random environments. I cannot see for the moment an easy way out to replace key point 1. Last but not least, one may inquire about higher dimensional versions of the problem. Devising a good two-dimensional model for random walks in really random media and generalized Lévy-Lorenz gas is itself a non-trivial and in principle not unique task, which would require a due study in the matter of recurrence and recurrence properties and functional limit theorems. Moreover, one should pinpoint meaningful and non-trivial first passage events in higher dimensions. In fact, for instance, you could have also the direct sum of two one-dimensional independent orthogonal components. And if you look at the first passage to half plane of the coordinate system, then you are trivially led to a one-dimensional result, since what really cares is the projection. But anyway, in recent years, the physics community emphasized that higher dimensional non-trivial first passage problems are of interest, for instance, by means of the equivalence of these processes with one-dimensional first passage processes involving multiple walkers. So this maybe could be an interesting issue to be explored. But that's all for today. Thank you for listening. And if you have any comments or questions, I will try to answer to the best of my knowledge.
Okay. Any question, comments?
Question. I'm not sure I want to be recorded, but let's go. So in one theorem, you had the two conditions, one or the other, and it was about it was gamma plus beta smaller than something, and my question was, I'm not sure I have correctly understood. Do you have two different proofs depending on the two things? And do you suspect that when you have equality, there is a kind of combination of the two processes, which can give rise to something? Well, what is your what happens if we have equality? Maybe something dominates in one case, something else dominates in the other. Okay. And if it is the same exponent, maybe it can combine when there is an equality case, but I guess it is more difficult. But no? Okay, you did not write it. you wrote
because when
smaller and larger, but not equal.
Because when you have the equality, essentially.
So you did it.
Is in the lemma.
Okay.
When you have that. You have two.
Okay, thank you.
You have gamma 1 and gamma 2.
Okay, so no problem.
Gamma
it's not a difficult case.
And they are equal, there is no problem.
Okay, thank you.
The only thing is that you have not matching bounds. because you have two different
Yes,
contributions
yes,
that
yes, yes.
combine.
You have the same order, but maybe not the
Yeah,
same
yeah,
constant, and so
Whereas
maybe
if
something
one-
can happen in tricade can happen in the constant, or no, it's easy. I just sorry.
Yeah, you can also write in some cases also the constant. Yeah, explicitly. We wrote it in the
Okay,
in the proof of the in the paper, but yeah.
okay, thank you.